Yeah, hello everyone. Yeah, I'm going to talk about the GPU-based tracking with ACTS on behalf of the ACTS group, in particular the ACTS R&D team. And you have already heard about the ACTS project from Benjamin's talk. And here are some reminders. So the ACTS is basically a modern open source high energy physics tracking toolkit. And as claimed here, is designed to be experiment independent, as in the name, a common tracking software. But beyond that, it's also an R&D platform to explore fast tracking techniques of parallelization and acceleration. And this is realized by a few different plugins as shown here. So the first, the AutoDiff, you have already heard about that. And then the CUDA plugin, which supports the heterogeneous computing with GPU. We also have the SQL for the similar purpose, and we can also use the SQL for the parallelization with multi-cores. And then we have the Microsoft-based Onyx plugin, and this is can be used for the deployment of the machine learning results for the tracking, which is very important. Since you probably have got an idea what GPU can mean to us from the previous talks about the GPU, so I'm just going to go directly to the implementation, and which is the focus of this talk. So the charged particle charged track reconstruction. So this is a very typical chain of the tracking. So which usually starts with some preparation of the data, like the space point formation. And then we have the process of track fitting and track finding to find and to estimate the track parameters of the tracks. So if we take the Kalman filter based approach, it usually requires some seeding, and then this is the purpose of the seed finding algorithm. Yeah, the Kalman filter is usually some fitting algorithm to estimate the track parameter, but it can also be extended to the combinatorial Kalman filter to find the tracks. And of course, the found tracks can be fed into the vertex reconstruction. And in this talk here, I'm going to talk about the GPU-based seed finding and the Kalman filter. So the CKF has not been yet looked at on GPU yet, but should be some interesting work coming in the future. So the ACTS seed finder is taken from Atlas, but with a lot of optimizations. So similar to other seed finders, it has the process of the formation of the space points. And then there's some binning of the space points based on the phi and z coordinates of the space points. And then we have the very classical doublet and triplet search to find the seed. And there's also some filtering of the wound seed. So this two process is designed in ACTS seed finder designed to be highly parallelizable, but this is only currently only partially parallelizable. So far the GPU, the ACTS seed finder has already been implemented on GPU with both the CUDA and the SQL1 API. And as I said, the main process ported on GPU is the search of the doublet and the triplet, as shown in those screenshots. And then the performance. So first, for sure, we have to make sure the fixed performance is correct. So we, as shown in this plot, which is the percentage of the found seeds versus the number of space points, which is basically 100%. So this is some validation of the results on GPU. And then we have the timing performance, of course. So these two plots here shows the performance, the timing performance of the seed finding on two sets of CPU and GPU. Basically, they are on different machines. So the gray colors here on these two plots are the timing on CPU with a single thread. So this is used as the reference test in those bottom two plots when we want to look at the speed up. And then the blue color is the GPU performance, which is tested with the integrated graphics card on the CPU. And then the green color are the GPU results. So when we look at the speed up, obviously, the NVIDIA GPU has better performance compared to the integrated GPU card. And one thing worth mentioning is that actually the CPU performance is expected to be competitive if with multi-cores, as we can see from these two plots, because currently we don't have shown the CPU performance with multi-cores yet, but this is something to come a bit later. And then the next tracking chain look at on GPU is the track fitting with AZTS Kalman filter. So some illustration of the Kalman filter design. So the Kalman filter is designed based on AZTS propagator, and the propagator is templated on the stepper and the navigator. So can be working for different tracking geometry and bit field. And then the Kalman filter is used in the propagator as an extended propagation options. So the track fitting or one track fit is basically a process of progressively updating the track parameter based on some matrix operations. And this usually includes two different steps. So one is the update of track parameter from one surface to another, or from one measurement to another measurement. So this has taken into account of the magnetic field. And this is done with the longitudinal stepper. And then you can see from this here that we have the transport functions here. And then when the propagation has reached the surface where there's a measurement that we think we can be taken into account in the filtering, the track parameter is updated or filtered using this measurement. And of course, after all of the measurement has been filtered, an additional smoothing step is included as well. And this is a very classical matrix operations in the Kalman filter. And
you have about 2 minutes to go.
Okay. So actually there's a third step, which is the material effects update, but this is usually integrated in the Kalman filter with the stepper. Yeah, so the track fitting parallelization strategy. So the first very simple and straightforward strategy is to parallelize the track fitting over the tracks, because the track fitting are independent. But because we have a lot of matrix operations within this one track fit, so this means heavy workload for one track fit. So if we want to look have better performance, we look a bit further to use multiple threads for this track fit. And so we can use multiple threads for the matrix operations. So this is also tested. And then the fitting results. Again, first to look at, because it's fitting, right? So we have to check if the parameter is fitted correctly. And this is done by looking at the pool of the fitted parameters at the parity surface. So as shown here, we have very good Gaussian distributions with expected mean and sigma for this. And then here the timing performance. So this is tested on different machines. Again, we have the gray color here on the CPU with one single thread, and then the orange color with 60 threads on the Haswell node with a total of 64 threads. And then the GPU results with either a one thread per track or one block per track. So if we compare the GPU with CPU with only a single thread, we can see that as long as we have like more than 40 tracks, we can see some speed up. But this is not the case if we with the multiple threads on CPU. So only we have hundreds of tracks, we can have some speed up compared to the CPU with multiple threads. Yeah, and we also see that we have better performance on GPU when we have more tracks by using just one thread per track, because a lot of threads are wasted with this approach. Yeah, currently we're still trying to optimize some matrix operations on GPU. Before I go to the summary, I want to briefly mention about the GPU-based geometry navigator. So this is inspired by the ray tracing for the computer graphics, because the navigation is basically the approach of asking for the intersections of the track with the detector objects. And to do this on GPU, we have to make sure we have the common representation of the geometry objects. So this is done by some meshing of the surface. Yeah, but currently we are still optimize this because we are suffer a bit from the overhead of the data transfer of the detector surface. Okay, the summary. So as shown, we have some prototypes of GPU-based tracking tools working, like the seed finder, the Kalman filter, and the geometry navigator. But we are still trying to optimize the performance on GPU. And generally, one code for all is difficult because it's GPU larger CPU. And we can, of course, have some speed up, but this comes at a cost because we lose some flexibility of the code, which is usually optimized on the CPU. But we are working towards some solutions. For example, in the standard HTS repository, we are trying to customize the scalar precision to use either float or double. And yes, more R&D is usually very important to understand all of those possibility and limitation. And if you are interested, just get in contact. We have some interesting projects going on. And yeah, that's all. Thank you.
Thank you very much. That's a nice presentation. And we've got time for questions. There's already one from James, so please go ahead.
Hi, so thanks for the very nice talk. So you said on slide 5, that you'd implemented this in both CUDA and also SYCL1 API. Yes. I was just wondering if you'd been able to compare the performance of these two implementations and whether you'd seen any anything interesting there.
Yeah, so I think Atina is the better person to answer this question.
Yeah, so this is something that we don't usually show because it's a little bit of an apples to oranges comparison, since the two algorithms are not exactly the same. The CUDA implementation is a little bit different from the SYCL implementation. Having said that, the CUDA implementation is about 10 to 20% faster than the SYCL one, then running on an NVIDIA card. So all of these results that you see here on this slide, these come from the SYCL implementation. So the SYCL code running on NVIDIA hardware. The native CUDA code is a little bit faster than this. And also, importantly, at small number of seats or small number of space points, the CUDA implementation becomes faster than the single-threaded CPU implementation, faster than the SYCL one does. It has smaller overheads, but as I said, it's not exactly apples to apples.
Okay, thank you. Thanks.
I did see a hand earlier from Ellie, but did you have something to ask, or are you satisfied?
It was the same question.
Okay, great.
Thanks.
Other questions? So we have a bit of time. Yes, John, go ahead.
Hello. I just noticed that the discussion of the geometry navigation. Of course, geometries for tracking are much more simplified than geometries in detector simulation, but it might be interesting to have a chat at some point about at least some of the potential commonalities. So it was more of a comment than a question.
Absolutely, John. If I can jump in there, it's a long-standing issue in our issue tracker is actually to try to use a vec.geom backend, yeah, for this, which should not be so difficult actually, because this is the TrackML detector, and we have implemented first for visualization this possibility to have every single surface triangulized, and from there I think it's rather easy to translate it in whatever plane definition you want to have. So this would be a really nice project to see whether we can join forces there, I think.
I don't suggest that we have something that's fast on GPU at the moment, but I agree with you that there is a significant commonality and understanding at what time it would be good to work together is a very important idea.
Yeah, so maybe we can have some discussions offline after this.
Yeah, ask actually a slightly related follow-up question. I think it's, yeah, I think it is. Does the triangularization mean that you're reducing the precision to an extent, or maybe, or does it complicate any, let's say, other detector geometries?
Yeah, go ahead, Xiaocong, if you want.
You go ahead.
Okay.
You're the expert.
Not really for something like a full planar type detector, because for tracking, because for tracking you anyway will simplify the support material on some let's say non-physical surface. So at that stage there is no clear simplification in there. The idea behind that is basically, the idea behind that was to have all surfaces represented by the same type, such that we could potentially really write a efficient intersector that goes through candidates basically blockwise. Yeah.
Thanks. Okay, so I think we finished the discussion there. Thanks again.
Okay, thank you.